Journey with us out beyond the familiar blue skies, past the planets and asteroid belts, into the deepest, darkest corners of the cosmos. Here, amidst the silent ballet of galaxies and the fiery birth and death of stars, lie objects of such immense power and terrifying potential that they challenge our very understanding of reality. For decades, one cosmic entity has reigned supreme in our nightmares, capturing the public imagination like no other: the black hole. We picture them as the ultimate cosmic prisons, gravitational monsters lurking in the shadows, points of no return where the laws of physics themselves seem to break down. They are the embodiment of the unknown, the inescapable abyss. Their names echo in science fiction, their properties, the event horizon, the singularity, the chilling prospect of spaghettification, fuel our deepest cosmic anxieties. But what if the darkest shadow has distracted us? What if the most famous monster isn't the only monster? What if there's something else out there, something born from similar stellar cataclysms, yet possessing a different, perhaps even more visceral kind of horror? Imagine an object barely the size of a city, yet containing the mass of one, maybe even two suns. A sphere forged in the heart of a supernova, spinning faster than a kitchen blender, radiating unimaginable heat and wielding magnetic forces capable of rewriting the rules of matter itself. This is a neutron star, and while black holes might represent the terror of the void, the ultimate endpoint, neutron stars embody the terror of extreme existence. They are tangible nightmares operating at the very edge of known physics, pushing matter and energy to limits that defy belief. Title card. So buckle up, fellow space enthusiasts. Today we challenge the cosmic horror hierarchy. We'll delve into the crushing gravity, the blinding radiation, the impossible densities, the hyperfast rotation, and the universe-shattering magnetic fields of neutron stars. We will compare their tangible, violent reality to the abstract, hidden terrors of black holes, their inescapable event horizons, their theoretical singularities, their infamous spaghettification. Prepare to question everything you thought you knew about cosmic dread, because today we explore why neutron stars might just be the true nightmare of the universe. Before we crown a new champion of cosmic terror, let's give the reigning monarch its due. Black holes are, undeniably, deeply unsettling phenomena. Their very existence pushes against the boundaries of our intuition, born from the death throes of the most massive stars in the universe. Imagine a star not just 8 or 10, but more than 20 times the mass of our own sun. When such a behemoth exhausts its nuclear fuel, gravity, the relentless sculptor of the cosmos, wins its final victory. The star's core collapses catastrophically under its own immense weight, crushing down into an infinitely small point. The outer layers rebound in a titanic supernova explosion, briefly outshining entire galaxies. But what remains is absence. A region of space-time so warped, so gravitationally dominant, that nothing, not even light itself, can escape its grasp. This boundary of no return is the infamous event horizon. Think of it as the ultimate one-way membrane. Information can fall in, but it can never come out. Cross that threshold and your fate is sealed. You are irrevocably bound to the singularity hidden within. But what is that fate? The most famous and perhaps most gruesome is spaghettification. It sounds almost comical, but the reality is anything but. As you fall towards a black hole, the gravitational pull isn't uniform across your body. If you're falling feet first, your feet are closer to the black hole's center of mass than your head. They experience a significantly stronger gravitational pull. This difference in force, known as a tidal force, stretches you vertically. At the same time, forces pull inwards from the sides, compressing you horizontally. The result? Your body is drawn out into a long, thin strand like spaghetti, torn apart atom by atom by the relentless gradient of gravity, a truly horrifying end. However, there's a crucial nuance here, one that will become important later. This dramatic stretching happens outside the event horizon for smaller stellar mass black holes. But for the supermassive black holes lurking at the centers of galaxies, millions or billions of times the mass of our Sun, the gravitational gradient at the event horizon is actually much gentler. You could theoretically cross the event horizon of a supermassive black hole without immediately being turned into cosmic pasta. The spaghettification would still await you, much closer to the singularity, but the initial crossing might be deceptively calm. And then there's the bizarre nature of time itself near a black hole. According to Einstein's theory of relativity, gravity warps not just space but time too. To a distant observer like us, watching safely from afar, someone falling towards the event horizon would appear to slow down. Their movements would become more and more sluggish, their light signals stretching to longer, redder wavelengths, eventually fading as they seem to freeze just outside the horizon, taking an infinite amount of time to actually cross. But for the unfortunate traveler themselves, time would feel perfectly normal. They would experience crossing the event horizon in a finite amount of time, plunging onwards towards the center. And what lies at that center? The singularity, a point of zero volume and infinite density where all the mass of the black hole is crushed. Here, our current understanding of physics breaks down completely. It's the ultimate unknown, the end point of gravitational collapse, a concept so extreme it borders on the mystical. What happens there? We simply don't know. Let's not forget, black holes aren't always black. When they are actively feeding on surrounding gas, dust, or unfortunate stars, they form accretion disks. This infalling material spirals inwards at incredible speeds, heated by friction and intense gravitational forces to millions of degrees. This process can make the region around the black hole one of the brightest objects in the universe, a quasar blasting out lethal doses of X-rays and gamma rays. Long before spaghettification, the sheer radiation from an active black hole's dinner party would incinerate anything nearby. An inescapable boundary, tidal forces that rip you apart, time warping beyond recognition, a singularity where physics dies, and potentially lethal radiation. Terrifying, absolutely. The black hole has earned its reputation, but is it the most terrifying thing the universe has conjured? Perhaps not. Let's turn our attention now to the black hole's smaller, denser, and arguably angrier cousin, the neutron star. If black holes represent the terror of absence, the neutron star is the terror of hyperpresence. It is not a hole in space-time, but a physical object of such staggering extremes that it makes planets seem like dust motes, and even normal stars appear tame. And like many monsters, its story begins with violence. We saw that stars over 20 times the Sun's mass collapse into black holes. But what about those slightly less massive, yet still gargantuan stars, giants between roughly 8 and 19 times the mass of our Sun? They too run out of fuel, they too succumb to gravity's pull, their cores implode with unimaginable force, triggering a similarly spectacular supernova explosion that blasts their outer layers across interstellar space. But crucially, the core collapse stops. It halts at a point of such density that it defies comprehension, leaving behind not a singularity hidden by an event horizon, but a tangible remnant, a neutron star. And when we say dense, the word barely scratches the surface. Imagine taking a star, 1.5, maybe even 2 times the mass of our entire Sun, and crushing it down into a sphere no wider than a city. This isn't empty space warped by gravity, this is matter. Matter compressed to a state found nowhere else in the universe, save perhaps for the fleeting moments of the Big Bang itself. The immense pressure during the core collapse is so great that it overcomes the forces separating atomic nuclei. Electrons are smashed into protons, merging to form neutrons. The entire star core becomes essentially a gigantic atomic nucleus, composed almost entirely of neutrons packed cheek by jowl. How dense is this neutronium? Let's try an analogy, though all analogies falter here. Take a single sugar cube, a teaspoon of neutron star material. Bring it back to Earth. That tiny amount would weigh roughly 1 billion tons. That's the weight of Mount Everest, compressed into the size of something you drop in your coffee. This isn't theoretical infinite density hidden from view like a singularity. This is quantifiable physical density that we can calculate and, through observation, confirm exists. It's the densest stuff we can actually see in the universe. And where there is such incredible mass packed into such a tiny volume, there is gravity. Gravity so intense it makes the surface of a neutron star arguably the most hostile physical location in the cosmos. Forget landing, approaching it is suicide. The gravitational pull at the surface is hundreds of billions of times stronger than Earth's. On Earth, mountains rise kilometers high, sculpted by tectonic forces against gravity's pull. On a neutron star, the gravity is so overwhelming that it crushes any irregularity flat. Sophisticated calculations suggest the tallest possible mountains on a neutron star, ripples in the ultra-dense crust, might be mere centimeters high. Any taller, and the star's own gravity would instantly flatten them. The consequences of this gravity are terrifying. Imagine hypothetically hovering just above this surface and dropping an object, say a marshmallow. On Earth it falls gently. Here, even falling a single meter, just over 3 feet, would cause it to smash into the surface at several million kilometers per hour. Drop it from higher up, it approaches significant fractions of the speed of light. The energy released upon impact would be equivalent to a nuclear bomb. Falling just 1 centimeter, the height of one of those mountains results in speeds so high they are difficult to fathom. The gravity doesn't just crush, it bends. Space-time is so warped near a neutron star that light rays passing nearby are severely deflected. In fact, the gravity is strong enough that light emitted from the back of the neutron star can be bent around, allowing us to see more than half of the star's surface at once. Under the right conditions, gravity can even trap photons in unstable orbits, forcing light itself to circle the star before escaping or falling back. And it's hot, unimaginably hot. Born in the fires of a supernova, a young neutron star's surface simmers at millions, perhaps even initially trillions of degrees Celsius. Even older neutron stars maintain surface temperatures of hundreds of thousands to millions of degrees. They don't glow with the gentle visible light of our sun. They blaze fiercely in high-energy X-rays and gamma rays, bathing their surroundings in lethal radiation. Crushing gravity, city-sized density weighing billions of tons per teaspoon, a surface where falling inches means relativistic speeds, bent light and searing X-ray heat. This is the static picture of a neutron star. It's a physical place of extremes that already rivals the conceptual horror of a black hole's interior. But neutron stars are rarely static. They are dynamic, spinning and magnetically charged engines of cosmic violence. The sheer physical presence of a neutron star, its density, its gravity, its heat is horrifying enough. But these are not static relics. Neutron stars are born spinning, and like cosmic figure skaters pulling in their arms, their rotation accelerates to truly mind-boggling speeds as they collapse. This isn't a gentle pirouette. We're talking about objects up to twice the mass of our sun, yet only 20 kilometers across, spinning hundreds, sometimes thousands of times per second. The fastest known pulsar, designated PSRJ 1748-2446 ED, whirls at an astonishing 716 times per second. That translates to over 43,000 revolutions per minute. Your kitchen blender, straining to make a smoothie, typically maxes out around 20,000 RPM. This city-sized stellar corpse spins more than twice as fast. This rapid rotation has profound consequences. Many neutron stars possess powerful magnetic fields. We'll get to just how powerful shortly, that are tilted relative to their spin axis. As the star spins, these magnetic fields sweep beams of radiation, radio waves, X-rays, even gamma rays through space, much like the beam of a lighthouse. If Earth happens to lie in the path of one of these beams, our telescopes detect a regular pulse of energy each time the beam sweeps past. This is a pulsar. These pulses are so incredibly regular, especially from older, more stable pulsars, that their timing rivals and in some cases exceeds the accuracy of our best atomic clocks on Earth. There's an eerie, almost mechanical precision to these cosmic beacons, ticking away across millennia, powered by the rotational energy of a dead star. But the rotation, as dizzying as it is, pales in comparison to the neutron star's most terrifying weapon, its magnetic field. When the core of the progenitor star collapses, the original star's magnetic field lines get dragged along and compressed into an incredibly small volume. Just as density skyrockets, so does magnetic field strength. A typical neutron star boasts a magnetic field hundreds of millions to trillions of times stronger than Earth's magnetic field, which merely guides our compass needles. Such a field would instantly erase every credit card on Earth from the distance of the Moon. It would distort the electron shells of atoms, forcing them into needle-like shapes. But this is just the average neutron star. There exists a subclass, a breed of neutron star so magnetically potent they earn a special name, magnetars. Magnetars are the true magnetic monsters of the universe. Through processes not yet fully understood, perhaps related to their initial spin rate or internal dynamo effects during formation, their magnetic fields become amplified even further, typically 1,000 times stronger than those of ordinary neutron stars. We're talking fields quadrillions, that's 1,000,000 billion times stronger than Earth's. This is the strongest magnetic force we know of anywhere in the cosmos. A magnetar's field is so powerful it dominates its environment and profoundly affects the star itself. The solid crust of the neutron star, composed of heavy atomic nuclei arranged in a crystal lattice under immense pressure, strains under the colossal magnetic stress. Sometimes this stress becomes too much. The crust fractures. These are starquakes, analogous to earthquakes on Earth, but releasing energies that dwarf anything our planet can produce. A starquake on a magnetar can cause a sudden reconfiguration of the magnetic field lines, extending outwards from the star. This reconfiguration unleashes a catastrophic amount of energy, often in the form of stupendously powerful bursts of gamma rays and X-rays. How powerful? On December 27, 2004, instruments orbiting Earth detected a massive gamma-ray flare. It originated from a magnetar known as SGR 1806-20, located nearly 50,000 light-years away, halfway across our Milky Way galaxy. In just 0.2 of a second, this distant dead star released more energy than our Sun emits in 250,000 years. The burst was so intense that, despite traveling for 50,000 years, it measurably ionized Earth's upper atmosphere, disrupting radio communications. A tiny star the size of a city halfway across the galaxy reached out and physically touched our planet. This is active, violent hostility on a galactic scale. Unlike a black hole, which primarily affects things that fall into it or get too close to its accretion disk, a magnetar can unleash destructive energy bursts that traverse interstellar, even intergalactic distances. But the magnetic terror might be even more direct, more fundamentally disturbing. Visual conceptual animation focusing on the atomic level near a magnetar show atoms approaching the intense magnetic field. The electron clouds are distorted, stretched into thin lines along the field direction, then show the atoms themselves being pulled apart. The magnetic fields near a magnetar are so strong that they warp the very fabric of space and influence fundamental particle interactions. Calculations suggest that these fields are powerful enough to literally tear matter apart, atom by atom. Not through gravity, but through electromagnetism. The field can exert such different forces on different parts of an atom's electron cloud, or even the nucleus itself, that it overcomes the forces holding the atom together. Some sources suggest this magnetic dissolution could happen to an object, like a hypothetical astronaut, from a distance of perhaps 1,000 miles, long before gravity would become the primary threat. You wouldn't be stretched by gravity, you'd be unraveled, atomized by the sheer magnetic force. Spinning at blender speeds, pulsing like cosmic clocks, wielding magnetic fields that can cause starquakes, launch galaxy-spanning energy bursts, and potentially dissolve matter itself. The neutron star is not just a dense corpse, it's an active engine of terrifying power operating under physical laws pushed to their absolute breaking point. We've journeyed through the crushing abyss of black holes and the violent, hyperdense reality of neutron stars. Both are undeniably terrifying products of stellar death, pushing physics to its limits. But now let's put them head to head. Let's revisit our central question. In the contest for the title of most terrifying object, why might the neutron star have the edge? First, consider the nature of their terror, tangibility versus abstraction. The horror of a black hole is profound, but largely conceptual. It lies in the unknown beyond the event horizon, the theoretical singularity where physics ends, the philosophical implications of an inescapable prison and potential information loss. It's the terror of the void, of ultimate endpoints. The neutron star, however, presents a horror that is brutally physical and, in principle, observable. It's a place, a city-sized sphere of tangible, albeit extreme matter. Its terrors, the density, the gravity, the heat, the magnetic fields, operate within the realm of known, albeit extreme physics. We can detect its pulses, measure its temperature through X-rays, infer its magnetic field strength. This tangibility makes the nightmare feel more immediate, less like a mathematical abstraction and more like a physical monster. Next, let's compare the surface versus the event horizon. The event horizon is the black hole's defining feature, the point of no return. Yet, as we discussed, for a supermassive black hole, the crossing itself might be uneventful. The tidal forces might not rip you apart until much later, deep inside the hidden interior. The initial boundary crossing lacks immediate, visceral violence. Contrast this with approaching a neutron star. There is no gentle gateway. Its surface, or the region just above it, is the zone of destruction. The moment you get close, you face the full fury of its billion-ton per teaspoon density, its relativistic speed-inducing gravity, its million-degree heat. There's no quiet entry. The violence is immediate, physical, and absolute, right there on the observable edge of the object. Then there's the aspect of active versus passive menace. A black hole, fundamentally, is a passive gravitational predator. Its danger lies in its inescapable pull. Unless it's actively feeding and generating radiation from an accretion disk, it simply sits there, warping space-time. Its influence is localized. A neutron star, particularly a magnetar, can be an actively hostile entity. It doesn't need infalling matter to unleash fury. Its internal magnetic stresses can cause starquakes, triggering colossal gamma-ray bursts that, as we saw, can affect planets tens of thousands of light-years away. Consider the modes of destruction. Black holes offer the infamous spaghettification via tidal forces and potential incineration by accretion disk radiation. Gruesome, certainly. Neutron stars match this with their own intense gravity, likely causing spaghettification much closer to their surface and searing surface heat. But they add a unique, arguably more disturbing method to their arsenal: magnetic dissolution. The possibility of being unraveled atom by atom, not by the familiar force of gravity, but by the alien strength of a quadrillion times Earth magnetic field, adds a layer of fundamental violation of matter itself. It's not just being pulled apart, it's being erased by an invisible force. Let's revisit density horror. The black hole's singularity boasts theoretically infinite density, a concept our minds struggle to grasp, conveniently hidden from view. The neutron star offers something almost more chilling: finite, quantifiable, observable density pushed to the absolute limit of stability. Knowing that a physical object the size of a city packs the mass of suns into something where a teaspoon weighs as much as Mount Everest, that tangible, almost comprehensible extreme can be more viscerally terrifying than an abstract hidden infinity. Finally, the spinning fury. Black holes can spin, yes, and their rotation warps space-time in fascinating ways through frame dragging, but the sheer, observable rotational velocity of a neutron star, hundreds or thousands of times per second, adds a kinetic violence, a sense of barely contained centrifugal force that is absent from the more static, absorbing nature often associated with black holes. It feels like a compressed engine perpetually on the verge of flying apart, even though its own gravity holds it together. So while the black hole represents the ultimate gravitational prison and the terror of the unknown, the neutron star counters with the horror of extreme physical reality. It's observable, it's actively violent through magnetism, its surface is an instant death zone. It offers unique ways to destroy matter, and its density and spin are tangible extremes. It's the monster you can see, and what you see is arguably even more nightmarish in its brutal physical specifics. We stand at the edge of cosmic understanding, peering into realms where matter, energy, space, and time behave in ways that shatter our everyday intuition. Black holes, with their silent, inescapable pull and the hidden mystery of their singularities, represent one extreme, the ultimate triumph of gravity, the conceptual horror of the unknown endpoint. But today, we've confronted its often overlooked sibling, the neutron star. We've seen how these city-sized remnants pack the mass of suns into densities so extreme a teaspoon outweighs mountains. We've explored their surfaces, not abstract boundaries, but physical locations of instant crushing violence and million-degree heat. We've witnessed their hyper-fast rotation, turning dead stars into cosmic lighthouses, and we've trembled before the power of the magnetar, wielding magnetic fields quadrillions of times stronger than Earth's forces, capable of triggering starquakes, launching gamma-ray bursts that touch us across galactic distances, and potentially even dissolving matter itself, atom by atom. So, which is truly more terrifying? The answer perhaps lies not in a definitive winner, but in the type of terror each represents. The black hole is the fear of the void, the inescapable trap, the loss of information, the journey into unknowable infinity. It's a passive, existential dread. The neutron star, especially the magnetar, is the fear of extreme presence. It's the terror of tangible physical forces pushed to unimaginable limits. It's the horror of observable violence, of active hostility, of an object that doesn't just swallow you, but can potentially reach out and affect you across vast cosmic distances with raw, untamed energy. It's a dynamic, visceral nightmare grounded in the extremes of known physics. Both black holes and neutron stars are awe-inspiring testaments to the power latent within the universe. They are the crucibles where our theories of gravity, quantum mechanics, and matter itself are pushed to their absolute breaking points. Studying them teaches us not only about the life cycle of stars, but about the fundamental nature of reality under conditions we can never replicate on Earth. They're reminders that the cosmos is not always serene or beautiful. It is also capable of violence and extremes that dwarf our comprehension. From the ashes of stellar death, the universe forges these monsters, one that consumes all into hidden oblivion, and one that rages against the dying of the light with unimaginable fury. Perhaps the true terror lies in the realization that such objects are not mere science fiction, but real, physical entities scattered throughout our own galaxy and beyond. The universe is wilder, stranger, and far more extreme than we often dare to imagine.